Hi, welcome to the Sage-based course on Monte Carlo methods. This is lecture 3.5 and we'll be covering indicator functions, probability mass functions and so on in this video lecture. The indicator function of an event A from the collection of events, or script F, or sigma algebra, is denoted by 1 subscript A. So here this 1 is a bold face 1. 1 subscript A is the indicator function of the event A, and its argument, say, is little omega. And if little omega, the outcome, belongs to the event A, if omega belongs to A, then this function, this indicator function of omega for the event A gives us 1. Otherwise, the indicator function simply gives us 0. Okay, if omega doesn't belong to A, the indicator function is 0. So it's not hard to see that the indicator function is really a random variable. For example, will it rain tomorrow in the Southern Alps? Okay, can be formulated as the random variable given the indicator function of the event, raindrops fall on the Southern Alps tomorrow. Okay, can you imagine what the little omegas in the sample space capital Omega for this rain falling experiment on the Southern Alps can be? You know, it's going to blow your brains out, right? So little omega could be every single way in which the wind blows all around the Southern Alps so that it precipitates into this event of rain tomorrow, right? There's quite a lot of details on the omegas here. So now let's look at the probability mass function. So recall that a discrete random variable x takes on at most countably many values in R, the real line. The probability mass function, or PMF, little f, of the discrete random variable capital X is little f of x, and it's defined to be the probability that the random variable, the discrete random variable capital X, actually takes the value little x, which is nothing but the probability of the set of all omegas such that x of omega is mapped to this value little x. Right? So let's look at a very nice discrete random variable called the Bernoulli random variable. So the Bernoulli random variable is a theta parameterized family of indicator functions of events of interest. Okay, so let's take an event A, like the one about whether raindrops will fall in the Southern Alps tomorrow, or an event whether the coin will land heads that we're about to flip, or whatever. Let the parameter theta, okay, denote the probability that A occurs. Okay, the event A occurs. So that is probability of A is this parameter theta. Okay, so the indicator function 1 sub A of A occurs is nothing but the Bernoulli theta random variable. So the model now we have is called the Bernoulli theta probability model with the Bernoulli theta random variable. So given a parameter theta in the unit interval 0, 1, which stands for the probability, this possibly unknown probability of the event A of interest, then the probability mass function, or PMF, for the Bernoulli theta random variable capital X is f of x semicolon theta. So the semicolon is here to point out that theta is a parameter. Okay, so the probability mass function little f of x for a parameter theta is nothing but theta to the power of x multiplied by 1 minus theta to the power of 1 minus x multiplied by the indicator function that either 0 or 1 is returned by x. Okay, so this particular thing here, indicator function subscript 0, 1 of x, simply gives us the value 1 if x is either 0 or 1. That is, if x belongs to the set, then this part will return us 1. If x is not 0 or 1, then this part will give us 0. Okay, so now if x is 0, then this part will give us 1. Okay, so what about here? x is 0, so 1 minus 0 is 1. So this part is just 1 minus theta to the 1. And if x is 0, theta to the 0 is 1. So this whole expression gives us 1 minus theta if x is 0. Okay, that's the middle thing here. Okay, if x is actually 1, then the indicator function will give us 1, because if x is 1, then 1 is an element of the set 0, 1. So this whole thing will give me 1. And if x is 1, the power here is 1 minus 1, which is 0. So this expression will give me something to the power of 0, which is 1. So this will have 1 times 1 when x is 1. And then this part will just be theta to the power of x, where x is 1. So this whole thing now evaluated just theta if x is 1. That's what this is basically saying. Okay, the top line here. So if x is neither 0 nor 1, then this expression gives you 0, as I said, so you simply get 0 otherwise. So this is simply the expression in the middle here for the probability mass function. It's a fancy way of writing the switch statement. Okay, so the probability mass function little f of x for the parameter theta is theta if x is 1 is 1 minus theta if x is 0 and 0 otherwise. Okay, and its distribution function, capital DF, is f of x semicolon theta, and that's 1 if x is greater than or equal to 1, and it's 1 minus theta if x is between 0 and 1 and 0 otherwise. Remember, the distribution function was already defined for you. It's nothing but the probability that the random variable capital X is less than or equal to this particular value, little x, and little x could be any real number here. So the semicolon is there because we want to emphasize the dependence of the probability on the parameter theta by specifying it following the semicolon in the argument to the probability mass function little f and the distribution function capital F. And we sometimes script by this unknown parameter theta to point out that the theta is actually not known and it's part of the parameterizing of the model itself. Okay, so that's quite a lot. The Bernoulli random variable is really a nice formal way to talk about probabilities of events. And now we'll go into for loops. So for loops are a very useful way that most computer programming languages provide to allow us to repeat the same action. Okay, in Sage you can use a for loop on a list to just go through the elements in the list, doing something with each element in turn. The Sage syntax for a for loop is, so you start with the keyword for, then we use a kind of temporary variable which is going to take each value in the list one by one in order. In the example below, we use the name x for this variable and write for x in my list. Okay, so after we have specified what we are looping through, we end the line with a colon. Okay, before I'm continuing on to the next line. Now we are ready to write the body of the for loop. In the body, we put whatever we want to actually do with each value as we loop through. Remember, when we defined a function and the function body was indented, it's the same here, right? So the body is a block of code which is indented. So the Sage standard indentation for block is 4 spaces. So you have to put the body of the for loop in a block with the same level of indentation. So finally, we indicate to Sage when your for loop has ended by moving the beginning of the line following the for loop back, so that it is aligned with the for which started the whole loop. Okay, so it's much easier to just go and do it in the cell here. The cell below gives a very simple example using a list. So we first assign to the variable my list this list of values 1, 3, 6, 4, 2. Here is, remember, the assignment operator equal to. Now for x in my list colon, right? So this is the colon and this is the keyword for, and remember x is that temporary variable that is going to store the values in my list. Okay, so this again is a keyword in my list. Okay, so this is simply the comment coming out. So this is confusing. You can move this a little bit like that. Okay, so now let's do that just to make it a bit cleaner. So now once you have done this, we have put 1, 2, 3, 4 white spaces to delineate this block, and we haven't really put anything in these lines, just to leave these comments here. And finally, once we are done with the for loop, all we're doing in the for loop is just printing the x. So that is just the body of the for loop. And finally, we're going back to the same level of indentation as the for keyword. And finally, we are printing the statement that end of my for loop. Okay, so here we go. End of my first for loop is the last statement, and we're simply printing all the statements inside. If we wanted to do this for any list, we could write a simple function that takes any list we give it and puts it through a for loop like the function below. So this is simply a function that makes your life a little easier. So let's make this a bit smaller. Here is the function, and it will simply take in a list and do the dirty work for you. So please go through these examples, try them, try the U-tries on your own, and you should be able to get a pretty good idea of for loops. The next video will look at conditional statements.